Hello everyone and welcome back to PCTE's New User Day. I'm William Ward, the New South Wales Manager with PCTE. I'm over here with Joel Shenoy on the board and our in-person attendees as well. Just so you know, these webinars are being recorded, and if you've got any questions, please ask them in the live chat, or if, when there's an appropriate time for a question, we can bring you up on a speaker so the whole room can hear. This is a session on rebound hammer testing that we'll be doing. So we'll begin by talking a bit about the history of rebound hammer testing and Schmidt hammers. And after that, we'll then be able to go on to a little more detail about the silver Schmidt versus the original Schmidt mechanisms and how they get used in practice. So first, a history lesson. The rebound hammer is one of the very first non-destructive tests available for concrete, and it is used primarily for relative strength of concrete in situ and comparison between different concrete. There are limits to Schmidt hammers that I'm going to go into, but probably the biggest limit to keep in mind as you work is that they are a relative strength, and the relationships that's built into them from the manufacturer may not be a good match to your materials on site. So that's probably the biggest lesson, is if you just take it and get an MPA, sure, but it's not going to be the most practical use of that tool. So what's a rebound hammer? Rebound hammer takes relates a rebound of a certain amount of force from the concrete surface, and we take a relationship between that force and the result an MPA, or we use it to compare similar things. So first things first, it's a surface test. You're not going to find out voiding halfway into a concrete slab with a Schmidt hammer or a rebound hammer. It's not appropriate. The original Schmidt mechanism was called the R value, or the R quotient, and that is the rebound strength. So what I mean by that is the height of the rebound above the initial strike, like that. So that would be an 82R read on an original Schmidt mechanism. Now, we convert that to compressive strength using a relationship chart like the one you see here, and that particular strength is going to differ on the pure mechanical original Schmidt design based upon if it's vertical up, vertical down, or horizontal. Now, if you are using one of the original Schmidt live models, that will handle the orientation of the hammer itself for you. But if it's mechanical, you do need to use a 3-line curve. Before we can talk about Schmidt hammers, let's talk about the actual MPA strength of concrete. The reason I do this is if we don't understand what we mean by compressive strength, we can't have a good discussion about what we mean by an in situ measurement of compressive strength. And that in Australia is the standards AS 1012.8 and AS 1012.9. 1012.8 covers casting the samples, and 1012.9 covers breaking the samples. So I've got a standard cylinder mold here, 2-to-1 ratio, 100 to 200 millimeters high, cylindrical, cast in stages of sample, compacted using either rodding, external or internal vibration, and covered and protected from the environment. Leave a cylinder out in the sun, it's not going to break the same way if it's protected. And the curing situation is we need to get it out of that mold, the solidified cylinder sample, between 18 and 36 hours, and we'll do so into a saturated lime water bath or a fog room at 23 degrees in the lower half of the country, or 27 degrees in the tropical regions in the top half of the country up in Queensland and similar. There's also some requirements in different transport authorities about different curing samples, wet storage, There's some road pavement examples where they'll actually put the cylinders into the concrete and cure it in the same amount of heating. There's lots of different variations of compressive strength. And the first thing you should understand is that if we treat that cylinder sample differently, or we cast a different geometry of sample, we're going to get a different outcome. All of this is very prescriptive. Compressive strength is not a material property. It's not a density. It's not a conductivity. It's a performance measurement based upon a very flowchart-like series of actions that result in a break. Now, when we break it, you'd normally at the 28-day mark, not because that mark has special significance, but because it's the same for everyone. So if you specify a 30 MPa mix and they break it 28 days and it's 32, it meets the criteria and every other sample's tested the same way. That's standardization. There is a need to flatten and prepare the sample, so grinding or capping, and also centered and with a particular pace rate. So the reason that I wanted to cover compressive strength testing is, well, you need to think about what are you going to do with a Schmidt hammer. Are you trying to replace a 28-day strength? That's not appropriate. You're not going to, we can bring up the video, Joel, number one. So we're not going to replace 28-day strength with Schmidt hammer testing. We're not going to replace 28-day strength with some of your maturity or other in situ strength goals. But we can supplement it, so we can do less cylinder breaks in some contexts. It's also where we don't have cylinder breaks, it can be a trouble solver. Most obvious example being if you've got lots of areas where concrete has been cast and you've got good records, and there was one region with missed records, comparing with the Schmidt hammer result, there's quite good. But if you've got a single pour, no one knows anything about it, and you give your client a Schmidt hammer test by itself, it's not quite enough to replace or substitute for that 28-day test. They're going to want something else, maybe some cylinder samples cut out and broken, core samples. So always remember the context of what you're working. Now, let's keep going with the Schmidt hammer. There's two commonly used kinds of Schmidt hammers, the silver Schmidt and the original Schmidt. There's also special purpose Schmidt hammers. So we're going to have Schmidt hammers used specific for rock testing and Schmidt hammers specifically used for paper testing. And there's a specialized pendulum hammer used for very weak concrete materials or cements or grouts, things like that. You also have, we can bring the, so we are going to want to test with any of these devices, because it is a surface test and it is dependent on surface finish, smooth and flat, either off form, ideally, or ground. It's also worth pointing out that a test taken on the side of a concrete element off form will be different if you take it from the finished top surface, because of the way the materials in the top are worked differently, cured differently than an off form finish. So there are two. For the silver Schmidt and original Schmidt, we also have two impact energies. So I mentioned that you have either, two kinds of mechanisms. We've also got two amounts of impact force. The type N, which is the standard type used for general purpose testing. If you don't know what you need a type N. If instead you have very weak or very thin concrete, the lighter impact force of a type L Schmidt hammer is appropriate, because if it's thin, it's not going to flex it, bend it, or break it. And if it's weak, it's not going to damage it. And it may, if we use something like the mushroom head configuration, also let us get to a slightly lower minimum value. The maximum values are roughly the same. Why don't we use a type L for every Schmidt test? It's because they're less repeatable. If we take a type L measurement and take a type N measurement, it's a little bit more dependent upon angle and position, and it can be a little more variable. With a type N, the heavier force results in a more predictable outcome. So we do have the special types. So first way to choose between your models is based upon the job you're doing. If you've got particularly high strength materials, that's a silver Schmidt mechanism. They run more effectively up to that 70 MPa or higher strength. The original Schmidt, comparable up to that sort of 50, 60 MPa. I'll explain why this is later, but this is just to help you choose the tool for the job if you want to bring one into your business. Type N and Type L I've already explained, also highlighting that pendulum hammer design is for very low strength, 0 to 5 MPa. We have in the ProSec Schmidt hammer range the original Schmidt mechanism, which we would, as purely mechanical, it will only give you the raw output. If you see the scale on the side, that is not an MPa scale, that is an R value, a rebound value scale. And similar to the mechanical pendulum hammer, that's a scale of a different rebound index. Then we have the data logging options. We have the original mechanism, which is still that rebound height. So if you've previously taken data or used in your organization an original Schmidt hammer, we can upgrade to an original Schmidt Live if you'd like data logging functionality, and all of your previous data sets are still appropriate. Now, the Silver Schmidt Live is the latest generation of the Silver Schmidt. We've previously had the Silver Schmidt PC and the Silver Schmidt ST. This is the direct replacement, the same mechanism, the same output, but both of these now go to our original Schmidt Live phone application. So this is the most commonly supplied Schmidt hammer ranges, and again, rock testing, paper testing, there's more specialized versions for that. Let's look at the original Schmidt mechanism. So the original Schmidt mechanism, we can see here that we extend out the impact spring, release the weight, and is pulled down to rebound off the plunger, and we measure that rebound height there. So that's the original Schmidt mechanism. There's some of the curves that you'll find in the manual, and the thing I want to highlight on all Schmidt hammer curves, some of them are made with cylinder samples like we use in Australia, and other curves are made with cube samples. If we go back to our compressor strength testing and we break exactly the same sample in a cube form versus a cylinder form, the cube form will break roughly 20% stronger than the cylinder, merely because of its geometry. The material is identical, the performance evaluation is identical, but the pressure, the compressive strength required to break it is higher. So watch out for these samples. The biggest warning I'd give you, on the sticker on the side of your mechanical original Schmidt hammers may be a cube sample. So watch out for that one. Now, the Silver Schmidt mechanism, meanwhile, we're still loading up a spring and we're still having our mass travel down and rebound, but rather than measuring the height of the rebound, there are optical sensors that will measure the speed of that rebound down and back. And that's what we're going to convert across to the Q value. This is the new index for the Silver Schmidt hammer. And that's going to have a couple of effects. Gravity doesn't matter anymore, can use it at any orientation. And we have a little bit more suitability, high strengths and low strengths. We also have a little bit less scatter. So if you were to consider your measurement standard deviation, it'd be a little bit smaller, all centered around the same result, effectively, the same response, but less scatter. And to show the reason we can go higher on a Silver Schmidt than on a original Schmidt, it's best seen with this curve here. Because the rebound, the R value for the original Schmidt grows fairly quickly as we go from up in strength, we increase the rebound value, it caps out lower. Whereas if we do the same measurement where it takes a slower growth in rebound value for strength, that means that there's greater differentiation. The easiest way to think of this is if we were, say, testing 60 MPa concrete with an original Schmidt, let's say we got 55 R value, and then I go to 60 MPa concrete, maybe I get 56 R value, less than one graduation on the scale. Much easier to measure it with an electronic measurement scheme, and much easier when it's got a couple more numbers in that Q index to compare to. This is why it's better at high strength. It's to do with the way it responds to the surface hardness. Now, the Silver Schmidt curves, when I show you a sort of standard setup I like, I'll talk about the original Schmidt versus the traditional reference N versus the lower 10 percentile curves. One thing I'll highlight is, since we've introduced the Schmidt hammer into Australia, some of the European standards that discuss Silver-Schmidt testing have brought in some new European reference curves that I'm not fully across, and I don't know how much experimentation there has been with them locally. So I'm still talking about the lower 10 percentile curve and the traditional N curve as I understand them. And that's what, but you will find if you look in the Silver-Schmidt live application, they'll put a little bracket, old bracket around them. If we could just pull just without the picture, Joel. What we've got going on here is, effectively, the lower 10 percentile curve is built such that if we look at all of the data points, for every 10 data points, only one of them is going to sit below the curve. The rest will sit above the curve. The idea of that is that it is inherently conservative. Rather than curve fitting a match to represent the middle of the data distribution, the curve fit is with all of the values, except for a small number of them, above the line, which gives us a conservative estimation of strength. It's intended to go somewhat lower than the MPa of the samples it was developed with. The traditional reference N is different in that it is built with younger, fresher concrete, so newly cast, and also without that inherent conservatism to it. So no manufacturer curve is fantastic, but the lower 10 percentile is at least a little bit on the conservative side. Both of these are cube curves, so you do need to use inside your Silver-Schmidt Live or PC/ST model a correction factor to convert cube sample to cylinder sample. I'll show you that when I show setting it up. Now, because the Schmidt hammer's been around so long, we do have quite a bit of different standardization about it. We have the American standard for C805, which is mainly concerned with the use of Schmidt hammers as a relative measure of strength between areas, and also a very clear definition of what a Schmidt hammer is. You'll find whenever I look at American standards, they tell you what something is. And whenever I look at European standards, they tell me how to use it. So that's the biggest difference I've noticed with testing standards between the two countries. So American standard, ASTM C805, what a Schmidt hammer is in relative strength comparison. EN 15204-2, how to collect Schmidt hammer rebound values, so R value or Q value. And then EN 13791, how to convert that across to an MPa, and also quite a lot of information about collecting samples on site and adjusting curves or creating your own curves for strength in situ. We do have some local guidance. It's not a standard, but the Concrete Institute of Australia does have their Z11 guidance for in situ strength of concrete. This covers Schmidt hammer testing, ultrasonic pulse velocity testing, along with securing and breaking samples from existing concrete together. It's the more correct place to begin if the job is, oops, we haven't got any cylinders and we haven't got any records. So do take a look there as well. Couple of limitations on Schmidt hammers. It's a surface measurement. It relates to hardness. So what if we had a way we could make the surface harder? That would be carbonation. So we'll talk about carbonation during our corrosion session this afternoon as well. But effectively what happens if you leave a porous piece of concrete out in the air for a long, long time, it will absorb carbon dioxide. That will have a couple of effects. It'll make it slightly more acidic, lowering its pH value. But what is more important for our purposes is for the same pressure to break it, the same compressive strength, the surface will become harder. So if we do a Schmidt hammer test, it will overestimate the strength. And there's a kind of, some of the Chinese standards look at conversions based on depth. There's also a procedure in the system manual and an option to use a correction factor. The intent being you test carbonated concrete and you cut or grind or sample down to uncarbonated concrete of the same type in the same place, and you get the ratio between them. So those are your options for carbonation. As always, it's mainly a concern for very old or especially exposed structures. So road infrastructure maybe would have additional carbon dioxide load, or if it's been there a long time. So, jobs of an in situ strength survey. What are we trying to do? Just like we talked about with the cover meter, what are we trying to do? With the GPR, what are we trying to do? With the Schmidt hammer, what are we trying to do? Are we comparing something we know to something we don't know? A good, maybe it's on a pillar 1 of 30 where there isn't a sample or there isn't a record, or it could be something like fire damage. This region has been degraded. Where does the degradation stop? Or are we looking at material strength? And I'll also highlight a difference between final in situ strength, essentially strength that relates to the performance of the structure, and early age strength, by which I mean how quickly strength is gained during curing, particularly relevant for things like lifting precast elements or trafficking concrete structures or removing formwork from concrete structures on site. You'll find this mentioned in contexts like concrete maturity, which is a temperature-based evaluation of in situ strength as well. This isn't a big presentation on this. I do have a webinar recorded on our YouTube channel that goes into more detail on in situ strength, but practically, the Schmidt hammer is another of the tools very commonly used in precast yards to let them know, yep, good to open the mould, yep, good to lift and good to traffic and work with. Or even if they're doing tighter quality control and they are breaking early age cylinder samples to make sure it's ready, why waste a cylinder sample? Check it with the Schmidt hammer first, then give the go to break the cylinder. Just gives a little bit more confidence. And like with any job, you want to know, what machine am I going to take out? Am I using its data logging? What do I need to get on site and what documentation do I need to do? And once again, I've got a webinar for this too. I have earlier this year, or was it last year, Joel?
It was this year.
This year, earlier this year, I had a webinar which was talking about preparing to mobilise to site, what to be ready, charge your batteries, make sure you know what you're doing, make sure you know what to bring, how to collect data and how to wrap it all up when you get back. So all of these considerations are good to do before even a simple job like a Schmidt hammer test. Now, accuracy of strength. Again, CIA paper has a little bit more of a look at this when that comes out, if that's accepted. But the guideline we've always given is if you've got a reasonable curve, your accuracy of the strength of the cylinder samples might be 5%, and that's good samples, but there's nothing is perfectly accurate. And the manufacturer's curve, 20 to 25%, if at all suitable, and we don't know if it's suitable. That's the biggest limit with the manufacturer's curves. We have an unknown we can't account for. Is the concrete and the local materials sufficiently similar to a European OPC mix, which they use when they built that curve? Or is it something exotic, different, or in some way not going to be appropriate? If you read the manufacturer's documentation, if you talk to me, if you look at your standards, all of them are going to tell you, no, go and make your own curves that match your materials. It's sort of easy for a concrete manufacturer to do that, or maybe a precast yard. I know it's more difficult if what you've got is site testing, but you can still do a process combining securing and breaking core samples with Schmidt hammer testing to achieve a more reliable confirmation of strength than you will using a curve of unknown quality. Now, the Silver Schmidt device we use most of the time is I like to consider this my default setting. I'm either going to look at my values as Q values, so that's where I just want the raw unit. I don't want any MPa conversion. The reason I do that sometimes is if a client doesn't need an MPa number in front of them, confusing them as to the reliability and accuracy of that value, they just need a relative strength conversion. Why give them a number they're going to think is perfect when it's quite loose? If I am doing MPa, that's fine, but I'll still want a 2-to-1 cylinder conversion if I'm using a manufacturer's curve. And I will typically go with the traditional N or the lowest 10 percentile curve, as I explained before. The final one you actually set on the hammer, so if you're ever looking for how to adjust the mean on your Silver Schmidt Live application, the setting is on the hammer itself, and that is a mean average. The reason I don't use one of the European or American standard settings I could have here is that attempts to control the average and the minimum and maximum results based upon the requirements of those standards. We're not, unless we're following those standards in our testing deliberately, using a mean average, it's just a schoolyard average, add your 10 results together or your 20 results together, divide them by 10 or 20, that's what the mean average is going to be. And then it'll convert it across to your MPA strength. I talked a lot about custom curves. How do we make them? So we want to have, I think, about 14 cylinder breaks minimum. Again, this is sort of a little bit of mental memory from the European standards that go into a lot more detail than I will in a 5-second overview. But we'll want to secure those cores, complete Schmidt hammer testing on the cores in a good solid V bracket or maybe in the compression machine before they're broken, and then break right away afterwards. If it's a core, test the concrete before the core is secured, crush the core as quickly as possible, and then fit a curve. There is a good manufacturer document that talks about the process to do this in Excel. It's not difficult, but you'll be able to extract a formula from your data points and then load that formula up into the custom curve functionality of your Schmidt hammer. So that custom curve functionality is then going to let you set the upper and lower bounds. And you want to set this as the lowest and highest cylinder break you've got, because we can't extrapolate the curve down or up. We don't know how it's shaped. We don't have the information below that point or above that point. And then that's loaded in the hammer, and it will produce an MPA conversion between those values, just like with the manufacturer curves, but it matches your material. It's also possible to go even more tight on your Schmidt hammer testing by combining techniques. So the particular example I've got here is combining ultrasonic pulse velocity testing. We'll talk about that a bit under ultrasonics, but combining a relationship based upon the speed of sound transmission in concrete with rebound factor from Schmidt hammer to broken cylinder samples. And what they've given as the example here is that they've achieved a correlation coefficient of 0.88 for the combined, whereas the Schmidt hammer would have been 0.78 and the UPV would have been 0.71 previously as a correlation quality. So the combination of the two gives a better overall behavior. And similar to how we build curves for Schmidt hammer testing, we could build curves for UPV testing, we could build curves for concrete maturity. It's the same process. You build a data set, you have simultaneous monitoring or testing of the data set, and after that, that all comes across. Now, final note on early age strength, just to highlight the performance that you could get from different techniques. The reason that people like a Schmidt hammer for testing is it's a simple thing, it's got no consumable parts, it's reasonably useful, and it doesn't damage a sample. So most early age strength testing is they break samples at 2 days or 1 day or 5 days, whenever they need to know the value. And that's fine, but what if the sample breaks low and there is a cost involved with breaking those samples? You also have the option of co-location of cylinders or match temperature curing. Both of these, rather than curing your concrete cylinders in the 23 degrees or the 27 degrees standard environment, they cure the cylinder either in the same environment as the concrete or in a simulation of the temperature inside the concrete to better develop the strength in that cylinder more quickly. So when you're braking for trafficking or lifting, the strength of the sample reflects the strength in the material as it is, rather than the strength of a perfect sample in a cold bath. So Schmidt hammer, we're also testing the real thing. And then there's methods based on temperature monitoring called concrete maturity, in which what is useful with concrete maturity is the sensors are temperature based and they can be placed at the points of critical strength. So if you've got a precast element with a lifting point where the forces will be largest, or if you're monitoring a more complex pour, the sensors can go where most appropriate to see the development. And these are used for things quite a lot to speed up high-rise construction all over the country and in tunnelling projects, and a lot of bulk temperature work as well. So that's the quick overview of Schmidt hammer testing. I'm going to open the door up to questions again, and we'll also maybe duck down and grab a Schmidt hammer if we've got time, and I'll be able to demonstrate its operation. But any questions first? Or comments, because I know some of you are out using these quite a lot and probably have your own insights to share.
Yeah, I'll ask a question.
Joel, if you just point the camera out, and you've got to go to number 2. Thanks.
So my question was around the actual use of the Schmidt hammer.
Mm-hmm.
I know when I was using it, I was getting different measurements based on how hard I was pushing the Schmidt hammer.
Yeah.
So what's the actual best process to
Best
use?
process, and I'll show this in a second. I'll just take 5 seconds to duck downstairs.
Yeah.
Well, Joel fills for time. Is you want to go in completely straight. So Joel, so you want to go in sort of at a 90-degree angle, nice and steady, and making sure you're on the flattest surface possible. So if you're going in off angle, over any kind of surface defect, it's just better to go smooth and controlled. There will always be a variation between individual impacts, but yes, there is actually an operator effect, especially if you're not gentle. The easiest way to have 7 people use it the same way is for everyone to be gentle, rather than everyone to be their personal version of rough with it.
And it would work overhead
Yep.
and down.
Though if it's an original Schmidt and it's not the ones that have the built-in distance conversion, there's a limit to that, because we've got to use the curve that matches the orientation.
Yep.
Behind you.
So I just wanted to clarify on the accuracy of the Schmidt hammers.
Yep.
So I think you mentioned something about 20 to 25%, or is it mainly based on how well it matches with the curve and all that stuff?
That 20 to 25% is it's not a calculated value. The thing about Schmidt hammer testing is, unlike some of our tests, we don't have to guess or use a specification for how good the relationship is.
Mm-hmm.
You can actually, when you do your statistics to build the curve, the same data set will tell you the quality of the correlation. That was some of those quality numbers I was giving you.
Yep.
The 20 to 25% was more of a guideline of that's probably roughly the quality level of your manufacturer curves, but it's or a curve you make yourself.
Yeah.
But you've got to make sure it matches the material, and that's the rub.
Okay.
That's the thing, because it's sort of we don't know if it's gone wildly off or it's a reasonably good match. That's where the problems come in. It's where you sort of sometimes get the effect of we're getting constantly higher or constantly lower results than we expected. It's just because that curve doesn't make a good match to that result. That's why some of the European standards will shift the standard curve up or down to have a better catch the behaviour.
So a lot of it is based on how rigorous you are with using the data and how well you do the curve.
Absolutely. Concrete, like the Schmidt hammers, are really good at relative strength, comparing one region we understand to one region we don't.
Right.
They're not anywhere near as good at giving you a definitive answer.
Right.
That's why we need all that evidence to back them up over here to start giving you numbers that mean something.
Gotcha.
But if we want to know that this bit is stronger than this bit, quite good, quite appropriate. And this is a discussion I'll have on the phone every day. Is we've got something we don't know the strength of. It's like, well, look, you could use the Schmidt hammer, but it's probably not going to be a great match to your material. Yep. Do you have a sample of that material somewhere you trust that is a known good to compare to?
If it does have that good relative strength, then could you then calibrate it potentially off something that you know, like strictly what the value is of their compressive strength?
Well, that's what we're doing with the curves, basically.
Yeah, right. Yeah.
Look, at a very loose level, which I don't really recommend, I'm sure a lot of the precast yards are just sort of almost getting a mental understanding. When we get a rebound value above X number, that mix is good. They may not even think in MPA, or they just may... They use them pretty roughly, pretty informally, just to help them make that choice. Because the exact number doesn't matter, but it being safe to lift and not being damaged or broken by lifting is very important to them. All right, Joel, yes, we have a question from the room. You've got to change yourself so you're audible.
Yep, we got a question from Reza. The question is this more suitable for hardness or strength test?
We don't really consider hardness of concrete the same way we consider hardness of metals. It's an aggregate material, it's more complicated. The test is much more like a hardness test we might do with metal testing, like lead hardness testing, but practically what it gets used for in industry is relative strength or trying to get MPA values for comparison as a surface measurement. The concept of hardness doesn't enter as much into performance of concrete materials. If someone in the room knows better than I do, you're welcome to answer the question as well, but that's been my experience over the years, is it's much more where people are doing it on strength conversions or as a backup to their compressive testing labs. Does that help, Reza? If you would like to unmute, we can bring you live. Yeah.
I had another question about the Schmidt hammer.
Yeah.
Can you use it like on a slab like this that has carpet over the top of it, or would it have to be directly onto concrete?
Yeah, it would definitely have to be on concrete. Like if you use it on carpet, you will notice that you'll get a value that's a lot lower than its actual compressive strength.
Yeah.
I guess along the same like kind of thing, then there's like a coating, like a concrete. Say you got like a coating or whatever, would that suit it?
No, unless it's like a really rough surface, like quite polished.
Yeah.
It'll damage the plunger.
Okay, we have a Schmidt hammer. I might be sort of struggling against how well I can show everyone this at the same time, but if you bring that screen up, if you bring up one of the videos that has, that should let the app. So this is the original Schmidt, this is the Silver Schmidt app. And now I'm trying to use a mouse utterly backwards, which is a real experience. If I go into ongoing, this is how I will be able to access my Schmidt hammer. So I'm going to go into the standard and I'll make that change to mean, like I discussed. So see, it's now a mean standard. And I can choose my conversion curve. So we'll go with the 10 percentile. And we'll change across to the MPa with the 2-to-1 cylinder, like I would like. Now, I'm going to test on the carpet. The carpet is not an especially good place to use a Schmidt hammer, so the MPa is going to be pretty meaningless. But if you grab the room camera, Joel, I can show the testing process. If you just point it over here. Thanks. So, come in at 90 degrees. And bring down. 27.0 Q. And as I take each strike, we can see that, we can hear that the Schmidt hammer is reading out the values. If you just change across to the presentation, please, Joel. And we can see that we are collecting the set of measurements. 25.0 Q, 27.0 Q, 27.0 Q. And we have in the green bar the average Q value and the conversion to 9.8 MPa, strong for carpet, meaningless in actual fact. But that's the basic operation of a Schmidt hammer. With the Silver Schmidt, we do need to then complete the measurement on our device to start the new file. In the Silver Schmidt applications, we also have the Screen Eagle data logging functionality you may be familiar with, so we can record images and notes and video notes, voice notes with our testing records. And that's going to be true on the Radar app as well and all the other Screen Eagle ProSec devices. And this is also the application where we can load up those custom curves and operate with. That's about what I've got to present on Schmidt hammers today. We will be resuming the next session on corrosion and half cell potential testing at 2:30, so a little less than an hour for the next session, but I've got a chance to take any final questions or comments before we go and wait for the next session.
I have one question.
If we get the mic. Thank you.
You have mentioned that we can generate the user graph.
Yes.
Actually, I have performed the Schmidt hammer test, but I don't know how to generate the user graph. Can you mention it?
So I'll share with you privately a little bit later, but if you go on the Screening Eagle website, or I believe it's also uploaded on our website, they have a PDF guide to use Microsoft Excel to develop the graph and also to produce the formula from that graph. So this is a fairly standard job you do in Excel.
Okay, thank you.
But yeah, I'll certainly make sure to show you while we have a break.
Okay.
All right. Anything else on the chat, Joel? All good. Thank you so much. I'll see everyone back again at 2:30.